How you guys doing today? Perfect. Good. All right. So this chapter, we're actually moving on to chapter 20. This chapter, this is actually quite short chapter. So I think I can finish this one by this Wednesday. But anyway, we can try. So we're gonna learn about carboxylic acid and nitro. So first of all, we're gonna learn about how to name those things. So if we have this, okay. So if you have carbonic groups here, it's not. The carbonic groups over here, the hydrogen group. In total, we have a carboxylic group over here. So this is a carboxylic acid compounds over here. It's pretty much the same thing what we've been doing for the compound naming. So you just try to count all the carbons over here. And then we have 3 carbons here, so it'll be propane. Okay. And then ornithine, propane. And then you just need to put the OIC acid. Because you have a carboxyl group there. So just try to find the base, which is the 3 carbons there in this carbon chain. So it's a propane, but we're gonna put the OIC acid because it has a carboxylic acid here. So you're gonna do propanoic acid. So if we have same, so if we have some substituting groups there, if you have maybe this one, okay? Maybe this one. So in this case, we're gonna count the carbon from here. 1, 2, 3, 4, and 5. Okay. So the thing is, whenever you have some substitution groups here, when you try to put the local number where you're locating your substitution group here, the carbon always start from where you have a carboxylic group over here, which is your number 1 carbon. So that makes your substitution group will be at what? 4. Because you always count the carbon from here. Okay. So if you count the carbon from here, you can give a lower number for this one. But in this case, we are gonna count the carbon in this carboxyl group always first. Okay. So in this case, this will be 4 methyl 1, 2, 3, 4, 5, right? So it'll be pentanoic acid. Makes sense, right?
Is that a dash or is in between methyl and pent? Is that a
Yeah.
dash or is that?
With this one, this is dash, yes.
Is the upper methyl?
Okay, gotcha.
Okay. So that makes sense, right? Okay. So let's try this one real quick. Maybe maybe you can try this one. Yeah, about 1 minute. Okay, about 1 minute. So yeah, this is a carboxyl group over here. You always count the carbon from here. That's the
Are you saying you always count the double carbon?
this carbon, yes. In the carboxyl group, yes. Yeah, perfect. So be 1, 2, 3, 4, 5, yes. Okay. So this one would be what? Okay. So this will be 1, 2, 3, 4, 5. So will be this position 2 after 3 and 4. So 3 and 4 dimethyl. And we have 5 carbons, right? So we pentanoic acid. Makes sense, right? We need one more. Okay, one more. Okay. So how about this one then? I'll do one more and we'll okay, but okay, about 1 minute. Okay, so yeah, this one will be back. We have you count the carbon from here, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So we obtain, okay. And then you have groups on the ethyl groups on 3, methyl group on 7, right? So, but we're gonna put this ethyl group first because alphabetical order, right? E, M. So it'll be 3 ethyl and 7 methyl octanoic acid. Makes sense, right? Okay. So this, I think we're good for this one, but let me give you a slightly tricky one. Okay. So if you have okay. You have this one over here. So you have a 2 carboxyl group here. 2, not 1. Okay. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. But we can also do 1, 2, 3, 4, 5, 6, 7, 8. Right. So in this case, you may not know which carbon you need to start from. Right. In this case, you can start from the one that has a lowest local number, which will be the tie still. So even though you count from here, it'll be 1, 2, 3, 4, 5, 6, 7, right? If you count the carbon from here, it'll be still 2 and 7. It's still tied. Makes sense, right? So then you have to go for the alphabetical order for your substituent groups. So this is methyl group. This is ethyl. So alphabetically, this comes first, right? E comes first and M. So you count the carbon from here. Okay, and then just one more thing. You have not 1 but 2. So you're gonna put not I oil okay, acid here. Sorry, here. But you're gonna put dioic acid because there are 2 carboxyl groups. So the name of this one will be, so still base is octane, right? Base is octane. And I'm going to put this one at 2 because this is close to this one with the E. So it'll be, let me actually write it. E ethyl 7 methyl. Okay. Methyl. And then octane. And then still dioic acid. Because you have 2 carboxyl groups. So this name is 2 ethyl 7 methyl octane dioic acid. Makes sense, right? Okay, perfect. All right. Whenever you're done copying, I'll move on to the next. All right, so I think we got some tricky ones. I just want you to remember one more thing for carboxylic compounds. So we have some carboxyl groups are attached to cyclic compounds, okay? And there's the other substituent groups over here. Whenever you do this one, you don't have to do oic acid anymore. Okay? oleic acid anymore. If you have a carboxyl group on the cyclic compounds, you can do carboxylic acid as your suffix, carboxylic acid. Okay, so I'll show you. This is always this one is 1, 2, 3, 4. Okay, this is where you bond to the carbon here. It's 1, 2, 3, 4, and this is where you have a hydroxy group, right? So it'll be 4 hydroxy, and this is a cyclo. So I'm gonna put cyclohexane. Okay, so it'll be 4 hydroxy cyclohexane carboxylic acid. Okay, and then if you look at the position, this is the dashed line, this is the wedge. So it means they are directing this way forward. This is going back up to this chalk, the blackboard here. So this is on the trans position, because this is in the cyclic compound. This is going up, this is going down, right? So you just need to do trans. So this is trans 4 hydroxy cyclohexane carboxylic acid. That's the name. Okay. So this is the exception. So if you have a carboxyl group attached to your not the alkyl groups, but the cyclic compound, you don't do the oleic acid anymore. Okay. But you can just copy carboxylic acid at the end. So let's try this one. Okay. Maybe you can try. Okay. Try this one. Okay, about 1 minute. Okay, so this one will be here, right? This is our carboxyl group over here, right? So I'm gonna just copy, and this is also cyclic compound, so carboxylic acid over here. And then this is methyl group, but this is on the number 2. So this is carboxyl group attached to this is your cyclic compound base 1. And so this will become 2, okay? So it'll be 2 methyl. And then this is also cyclohexane. Cyclohexane, so it's 2 methyl cyclohexane carboxylic acid here. And also this is on trans position 2, right? So it'll be trans, so it'll be trans 2 methyl cyclohexane carboxylic acid. Yeah.
You don't need to put like ortho or anything like that?
If you do, you can do author instead of 2, yes. But if you can do 2, you don't have to add an author. It's perfect. Very good. So if I did this one, it could have been what? Cis, right? Cis. Yeah, that's the difference. Cis. Makes sense, right? Okay, just one more. I will do one more and move on. So if you have this one, okay, over here. Now you have a cyclopentene. Okay, so in this case, you're gonna cut the carbon from here anyway. Okay, here. So this will be still same carboxylic acid here, and then And now you have to number your double bond, which is here's 1, 2. So your location for double bond is 1, right? So it'll be 1 cyclohexene carboxylic acid. Okay, so that's it. So because of the carbons right here, you just need to number your carbon. So if you don't have a carboxylic acid, you don't have to number it because it's automatically 1 over there. Yeah.
So is this cyclohexene or cyclohexene?
Hexene, because you have a double bond in here, right? So we're gonna put E and E. It will be not A and E. But because of the carboxyl group, you have to number where the double bond is. So we put. Make sense, right? Good. I think that's it for the carboxylic acid. So how about we do nitro? Nitro, we have this one. It looks like. Okay. Okay. So this one is also quite simple. You're gonna count the carbon from here always. So 1 here. This is the nitro. Okay, nitro over here. And then to count the carbon from here, because it's 1, 2, 3, 4, 5. This methyl group will be on the number 4. Okay. So it will be 4 methyl. And this is a 1, 2, 3, 4, 5. So it'll be pentane nitro. Almost same, right? It's almost same. Just you count the carbon from here because it's a nitro group here. So you have a 1, 2, 3, 4, 5, and that's it. So this is very similar to what we did for carboxylic compounds. Okay, and then there's a. Let's do the cyclic one too. Okay. So if you have this one. Yeah. So in this one here, it's pretty much the same too. For this one, so we have a nitro, right? For other alkyl compounds, but for this cyclic compound, you also do carbo nitrate instead of just nitro. It's like for carboxylic compound, you do not oleic acid, you do what? Carboxylic acid here. Same. When you have this group on the cyclic compound, you do instead of nitro, you can do carbonitro. Okay. So if you do this one, always this is the start point where you have this is your base. So the carbon attached to your the nitro is always number 1. So this will become 1. This will be 2. Okay. So it'll be 2, 2 dimethyl. 2 dimethyl, and then you have a cyclohexane over here, right? So the cyclohexane, and then not nitro because it's a cyclic compound. You do carbonitrate instead of just nitro because it's a cyclic compound. All right, makes sense, right? Okay. So I have just one more thing for this one. Okay. That is because it's the exception. There's some exception you can try. This is looks like. Okay. So this is okay. Here's the thing. So in this case, you're not counting carbon from here. because you have carboxylic group derivative groups over here. So it's not carboxylic group, but it's like with this R group, carbonyl group. So like there's some like also ethyl group attached to it here. So it's not carboxylic group, but some derivative form of the carboxyl group. Then you actually count the carbon here, not here, because this overrides the position of the nitro. So this is exception. Okay, so in this case, it's pretty much the same. You count the carbon from here. So 1, 2, 3, 4, 5. Okay, so your group is actually this nitro group is 4. Okay, but we have this one as your like a suffix. So we have a special name for this one. You might heard this already from last chapter. Cyano. Oh. Cyano. Yeah. So, do you guys remember this? So this is 4 cyano. We 1, 2, 3, 4, 5. So it'll be 10, no, 8. But this is you have one methyl group from the ester group. So we put this one is ethyl group over here, methyl group over here. So it'll be methyl 4 cyano pentanoate. I hope that, yeah. Let me give you one more example, okay? Let me give you, does it make sense though? Yeah, go ahead.
Why is it called pentanoate instead of like?
Oh, so because this is an ester group, this is so you have carbon O and R here, right? This one. In this one we call it ester group, and we usually put the OAT. So this is why this is not a carboxyl group. So let's try maybe one more. Maybe you can try. Okay, let's try this one. Try. And then let's try. Okay, this is. You can try this one. So this is the exception. You're gonna start the counting carbon from here, actually not there, because it's also carboxyl group derivative form, which is formed the ester group. Some tricky part, but you'll get used to it. So yeah, here. So you have the ester group over here. So you're gonna count the carbon from here, 2, 3, 4, 5, and 6. So I'm gonna do here. So 5 cyano, and 1, 2, 3, 4, 5, 6 will be hexane. And then no 8 here, and then you have a ethyl group here, right? You see the ethyl group here. So I'm gonna put ethyl 5 cyanohexanoate. Okay? That's the exception you can. Okay. Can I move on or do one more? Okay. So that was for the nomenclature. So we're gonna talk about some characteristics of the carboxyl compound first. So one good example I can give you is this one. So they can actually form So the carboxylic groups that has a hydrox group and carbonic group, they can form like a dimer. What I mean is there are two compounds kind of linked in a very strong hydrogen bond. So this is a You see, there's the two. These two bonds are we call the hydrogen bond, right? Do you guys remember the hydrogen bond, right? So the hydrogen bond is very strong intermolecular force, which can be formed in your carboxylic compound together. Okay, so they call it like a very good dimerism over here with the hydrogen bond. So usually they have a quite high boiling points. Okay, so acetic acid boiling point is almost like a 118, which you can compare to the other alcohol with the ethanol with a similar size. I think it's about like 78 Celsius degree. So this actually explains why those carboxylic compounds may have a very high boiling point, because much stronger hydrogen bond they can form in the intermolecular interactions. Okay. So and there's one more thing about this carboxylic group. Why it's so special is they have. Okay, let me make sure to give this copy down right here. So if they have a carboxylic group, oh, it's not this one. Oh, it's this one. So this is. I think you can also remember we talked about the alcohol last time. They can also have like a weak acid. But if you compare this one to carboxylic group, I'll show you the pK value. Okay. So if you look at this one over here, this is alcohol and this is a phenol that we know they also can behave like a weak acid. But even carboxylic group over here can do a better job as like a strong acid. But obviously it's not strong as a really strong acid. But compared to the alcohol, where they form the alkoxide by donating protons, they do even better job being carboxylate. So this is actually very low in pK value compared to the alcohol. Okay, not quite close to the very strong acidic solutions, but this is a very, relatively speaking, quite stronger weak acid than the alcohol. So here's something I can show you. Actually, can you guys guess why this become more stronger acid than alcohol? Even though it's still weak, relatively speaking, to the very strong one. It's because of this one. So if you have formic, this is the formic acid. Sorry. So when they become carboxylate, so when they lose the proton in the carboxylic form, they become carboxylate. They will become this one, right? Okay, so this will become formate, carboxylate, ATE, and then when they treat it with a very strong base, because it's a weak acid, they can actually form carboxylate. So when you look at these two, this carbon is bound to oxygen with the double bond, and this is the single bond with the hydroxyl group over here, right? But when they lose the proton, it's negative charge. But what can you possibly think about this one? These two. Do you think about something? Do you remember Do you remember the resonance structure? So yeah, so if you have a, okay, so if you have a one electron can be assigned on out of two. So it could do this one too, right? So what they do is they delocalize with the whole thing just become positive. So in that way, because of the resonance structure, it can be more stable. If they can be, relatively speaking, more stable than the alcohol, because alcohol can do this one with alkoxide. This can be quite stable, so they don't mind donating the proton than the other alcohol compounds. Kind of makes sense. Okay, so but anyway, so the carboxylic compound will have a quite high boiling point, but also relatively speaking stronger weak acid than alcohol because of this resonance structure they can do, and in form of the carboxylate over here. Okay? So what you normally do is we normally use Ka, which is this one. Okay? So in this case, this one. Okay, so this is A minus form. This is HA. So for your weak acid, you can do. Well, there's a water there. Okay. So you can do this one. So this will be looks like one. After donating the proton, which is conjugate base form, right? And this is your carboxylic acid form here. This is this one, and this is this one. Okay. So if you put the p value, pKa, which will be what? Which will be negative log, right? P value means negative log. Okay, so negative log. So you can actually separate them like this. So pKa should be equal to negative log of hydrogen cation, which is, we consider them as same as hydrogen protons, and the negative log of this one, conjugate base, your carboxylate after donating the proton. Over weak acid, your carboxylic compound. Okay. So if you think about this one here, this is the same as proton, right? Because it's just with water. Okay. So negative log of hydrogen cation is same as negative log of proton, which is what? Negative log of hydrogen cation concentration will be pH. Okay, so then this can be pH. Okay, so then what you can do is you can try to move this one. So this is a positive. So it would be pK minus pH will be negative log of the carboxylic groups. And then if you just do the other way, okay, so we can do the negative this one. So that makes the pH equal to pK plus log of your conjugate base over carboxyl, which is a carboxylate and carboxylate. So I'm not gonna do the mathematical problem for this one. It will be too hard. But I just want you to remember the equations, Henderson equation. That's it. So if you remember the Henderson equations, you'll be just fine. Okay? You don't have to worry about the anything. Henderson equation. I just derived from there. But that should be just fine. Right, so let's move on. Okay, so here's a couple of things I want to mention. Is if you have some compounds with the carboxyl group, okay? And you have another compound okay? You have another compound. This one. Oh, actually, let's make it look straight. Okay, so if you have this compound over here, you have a carboxyl group on the right side. But the only difference is you have a neighboring carbon that has only hydrogens or carbons over here. But this one has what? Hydroxy group here. And this one has very electronegative element which is fluorine over here. You see the sign? This is mean by acidity, meaning this is very strong acid, stronger acid than the other two, and this is stronger than this one. Can you actually guys guess why? So if you look at this is obviously the one that would donate the proton from here, here, and here, and then what would it be? This one would be stronger than the other two, and this would be the weakest one among these three. So if you look at this one here, there's not much thing you can do with helping withdrawing the electron to this side. Okay? So if you can make this electron density toward to the your more like carboxylate part of your compounds, that makes the oxygen can be easily detach the hydrogen as in the form of protons, because this will help for the withdrawing. So if you look at the hydroxy group carefully, this is actually what it looks like, right? And then obviously oxygen is more electronegative than hydrogen. So when they donate the hydrogen, they donate actually proton. That's why they become acid compounds. But to do that, they need to pull these two electrons to this way. But if you have some hydroxy group, which can also withdraw also kind of electronegative groups, they can actually kind of help by like on the neighboring carbon. But this one even more dramatic. So you have a very strong, very high electronegative elements falling on this carbon that help this oxygen to bring those two electrons between these two, oxygen and hydrogen in the hydroxy group, to here, so they can be donate the protons there. Okay. Does it make sense? Kind okay. So maybe so this is what we did on chapter 16. I will just give one more and I will just finish today. Okay. here you have a benzoic acid here. Okay. So only difference is they have a sort of a electron donating groups. Do you remember this electron donating groups here? And they're just nothing, just but hydrogen as a reference. This one is what? Electron withdrawing groups. Okay? So we have electron withdrawing groups over here. So it kind of makes sense that this one is more like donating the electron to this way, because this is electron donating groups, as we learned in chapter 16, right? But this is just hydrogen here. But this is actually electron withdrawing groups. Nitrogen group will actually try to push the electron density to this way. And then it makes this oxygen much easily can steer this electron to this way. So they will become carboxylate much easier, meaning they don't mind to donate more protein than the other two, relatively speaking. Kind of makes sense, right? Kind of. So I'll just stop here today.